Hi, in this video I will try to explain to you the types of variables that exist, and then I will explain to you one of the simplest statistical analyses that you can do when you have a data that is generated from a clinical trial or in a lab setting. Whether your data generates from a clinical trial or whether it generates from a survey-based study or whether it generates from a lab setting, the principles that will apply remain the same. So here I just give an example of a clinical study meant to assess the whitening efficacy of product ABC. So I just use a fictitious name. So the design of the study is the simplest that you can imagine. It's a before and after. The values, the observations that we see, that we record before the study, that is at baseline, before starting to use a treatment, will serve as the control. Now, the objective, as I always tell you, is very important. You always write the objective correctly. So here, I try to formulate some ways of writing it by saying that the study is meant to assess the whitening efficacy of ABC through chronometric measurements after 28 days of use. You could break this into two by saying the objective, a bit like the title, saying that it's meant to assess the whitening efficacy of ABC, and then the efficacy criterion would be chronometric measurements, in particular L values, for example. So let us look at this data set. Okay, so this is what we call a data set. We can also call it a table, or we can also call it a listing, right? These are the terms that are used, I would say, concurrently in the literature. Now, there are different kinds of variables that we have in this table. For example, gender, if I've got male here, so gender is one variable because it's going to vary, male, female, male. Now, if you have only female in the study, then gender is not going to be a variable, it's going to be a constant. Now, you're going to have similar cases like that, similar variables or different variables like age, for example, phenotype, that is the skin color, it could be 3, 4, 2, etc. This is systolic blood pressure, 120, 132. Now the L values, as you know, in the chronometric measurement, when we say L, when L increases, it means that the skin is fairer, that is more luminous. Try to think of L as standing for luminosity. So normally, L values turn around to be between 45, 48, 50, 52, 56. That's all. And the higher the L, the more luminous the skin or the apple or the rat, whatever you could be measuring the color. So I would say, let us say 56 here. And then this is at baseline, and then this is after 28 days of use. Imagine that it increased to 59. Now the skin clarity, we are going to think of skin clarity as a sort of a score between, let us say, 1 to 7. Now, when I say between 1 to 7, given that the name of the variable is skin clarity, when I say a big value for skin clarity, would mean the skin is very clear, extremely clear. It cannot be the other way around. It cannot be that 1 stands for very clear skin. No. So it's got to be 7 should be very clear, and here not clear at all. Okay? So this is the least favorable opinion, and this is the most favorable opinion. Depending on what is the name of the variable, this influences the the choice of whether a lower value stands for the least favorable one or it has got to be the other way one. Would you buy, okay, so values 1, 2, 5, etc. Would you buy the product? So this can be in the form of a yes and no. So 1, 0, 1, 1 meaning yes and 0 meaning no. So this is an example of a data set that can occur as a byproduct of a clinical trial. The point that I'm trying to make is that we have different sorts of variables here. You will realize that you have got one kind of variable that are numbers. These are numbers, right? All these. Okay? I will come to this one. While gender, male and female, here it's yes and no. These are not necessarily numbers. I can give a code. This is coding. I'm saying 1 stands for yes. But it doesn't mean that 1 equals to yes. No. Yes is a yes, 0 is a no. That's all. This is just a code that I use for the sake of data entry. And that's all. And for the sake of statistical analysis. The same thing for gender. So gender is not a number, while systolic blood pressure is a number. The L values, these are numbers. So here, you have to realize that we've got two sorts of variables. We've got two extremes. On one extremity, you've got variables that are purely numerical, and on the other side of the spectrum, you've got variables that are purely categorical. Right? Purely categorical. Like 1, 0, that is yes and no. Male, female. These are purely categorical. Numbers, these would be here. These variables would come here. Age as well. Now, between these two extremities, there is one which is a bit, I would say, ambiguous. This in the middle here, we call it ordinal. For example, skin clarity on a scale of 1 to 7, the values that the parameter can take are very limited. 1, 2, 3, 4, 5, 6, 7. It's not like L, for example, chronometric measurements which can take infinite values within a range. This one you will have only specific values. 1, 2, 3, 4, 5, 6, 7, and that's all. When we've got this kind of variable, it doesn't fall into numerical, it doesn't fall into categorical, it falls somewhere in between. It's called ordinal. Here. So this one will be here. The same thing for phototype. This kind of variable would be in fact ordinal. Okay? Now, why I'm telling you that, it's simply because the way that we deal with a variable that is numerical is not the same as the way we deal with one which is categorical. For example, I don't do an average here and I get 0.6, or I do an average here, I get 0.7, and then I say average gender equals to 0.7. It doesn't make sense. What I have to say is 70% are male and 30% are female. This is the correct way of doing things. I would say 80% of respondents buy the product, or something like that. I don't do averages or standard deviations here or here, but I do it here. I do it here. So, numerical, even the statistical analysis that we do later on, it will depend mostly on the nature of the variable, starting from simple descriptive statistics, that is mean, median, standard deviations, or even the counts and percentages. So starting from the basics to the most complex statistical analysis that you can do. It depends largely, mostly, on the nature of the variable, whether it's highly numerical, is it categorical, or is it in between. Now, the one that is in between, on some occasions you can treat it as numerical, on some occasions you can treat it as categorical. This one can move. Okay, with a degree of flexibility, you can easily move this one. But otherwise you've got these two extremities, but you have to try to stick to their nature. So I have filled this table with some fictitious values, just for us to have something to work with, and you can have a fair idea of how you could go about conducting a statistical test, or more precisely, understanding what's going on while you are reading a report. As I told you, every time, for any clinical trial or even a lab experiment, you have to report the sample that was used, that was part of the experiment. So in a clinical trial, you will report how many male and female you had, what was the age distribution. So here, this would be the count and percentages: 30% male, 70% female. Average age was between, 30 plus or minus 2, so you can compute the mean and the standard deviations. Phototype, you're going to report it in the form of counts and percentages. This one, most probably, you would do it using the means and standard deviations. Now, you can also choose to categorize. That is, you can say you want to categorize how many subjects had a systolic blood pressure lower than 120 and how many above that. So this is what we would call an original variable. This is the original variable, and from that you can create a derived variable. So a derived variable is simply one which is drawn from original values observed in an experiment. For example, with chronometric measurements, you have got the L, A, and B. These are original values, while the ITA is a derived variable from L and B. The delta E is derived from L, A, and B. One more thing you have to bear in mind is that the values that we produce is not necessarily one value. It could be an average of replicates. If you have done, you have been reading the color using an instrument, you could have done it 3 times just to avoid human error or pressure that you exert while doing the experiment. Just to be sure about the value, you can take it 3 times, and this could be an average. Right. So the main focus of this study was to see whether the color of the skin has changed from baseline to D28. Now, what you can do, a simple thing that you would do, any one of you, is that you can report the averages. That's the simplest thing that you can do. That is, you say, okay, D0 and D28, you can report the average, and you can report the standard deviation. That's very simple. If you go into Microsoft Excel and you use the function, or if even you can use the user-friendly tools that are already available in Microsoft Excel. For example, here, if you use the function equals to average of all these, that is all these, you are going to get the simple average here. You can also use the function equals to standard deviation. I prefer to use the one with point S, but it's the same thing. So equals to standard deviation of, you just select all these values, and it's going to give you the standard deviation. So when I get the averages from Microsoft Excel, you can even use your calculator, you can even do it manually, you will find the averages to be like this. So I can write a simple conclusion that skin luminosity measured by the L parameter, was found to be higher on D28, because this is D28, it was higher than D0, was found to be higher on D28 compared to 51.2 at baseline. The plus or minus standard deviation gives an idea of the level of variation that was present in the data. So it's an important finding as well. The next question that we ask is whether the change was statistically significant. You know, this change that we see here, we can even note it on 2 subjects or on 3 subjects. Is it enough to make a conclusion? Not necessarily. As I told you during our last conversation, that small differences, you have to evidence it with large samples. While big differences, you need just a few, a small sample size can be enough to evidence a big difference. So the question that we are asking ourselves is, okay, we have seen a change, but is the change statistically meaningful? In the sense that, do we have enough values in our sample to be able to support such a claim that luminosity has increased? And this is why we are going to conduct a statistical test. Now, the right statistical test that we are going to conduct here normally is going to be the paired students t-test. Why do I say paired? I will try to make the difference between the paired samples and independent samples just after. Why paired? Because the values that we see here, they are paired in the sense that it's the same individual. Their gender is the same. They are most probably of the same age because, well, maybe during the period of the experiment the age changed, but this is quite unlikely. The phototype is the same. They have more or less the same style of living. Their blood sugar is the same. There are so many things that are common between these two values. Their parents are the same. They have the same skin color. They react in the same way to the sun. So many things that are common to them. So we are going to use the paired t-test because the sample is paired. And the paired t-test compared to the independent sample t-test is more powerful to detect differences between two groups. So here it's not two groups actually, it's two variables, but they are the same individuals. So here we are going to conduct the paired students t-test, and maybe when I contrast it with the independent samples one, it's going to make more sense. So how do you do that? It's very simple. In Microsoft Excel itself, you can compute the average very simply by using the function equals to average. You can drag this like that. You can compute the standard deviation. Here we go. Now I can do a small graphical illustration rapidly. My interface is, because I'm operating from a MacBook, is slightly different from yours, but the principles are the same. Now, as you can see in this graph, there is something that we call a lie factor. I'm going to write it. There is a lie factor. What is the lie factor? Is that we are giving the impression that there is a big change when there is in fact just a small change. This is because of the scale that we choose, that automatically Excel picks up while drawing this kind of chart. I would ask you to change it, and the minimum value that you choose is usually the minimum one that you can observe in a sample, for example, or generally what you can observe. For example, L values, I have never seen L values less than 30. So the minimum that it could take is in fact 30, and I'm going to modify this by changing this. So I'm going to format the axis by changing it to 30 here. So when I change it, it shows me reasonably a more realistic picture of what is happening. There is a change, but not so much. I can include error bars here as well, but I'm going to skip this for now, not to make the explanation more complicated. So this is the change in skin luminosity, I would say L over time. So this is 1, 2, it doesn't make sense. It should be D0, D28. So you can modify this quickly as well. The horizontal axis should be like that. And that's it. So D0, D28, I'm gonna make it a bit bigger. Okay, like that. So that's correct. Can delete this. So these were our averages, these were our standard deviations. So now I'm going to compute, I'm going to do a t-test. So equals to t-test. The first array, so I select all these with my cursor, I click and drag, comma, second one, comma. This is a two-tailed test and it's a paired one, 2,1. Close, and that's it. My p-value is not statistically significant, right? Because it's bigger than 0.05. So what we know already is that when the p-value is less or equal to 0.05, we tend to say the change, the difference is statistically significant, and greater than 0.05, we say not significant. So here, 0.192 is greater than 0.05, meaning that despite we are seeing there is a change from D0 to D28, despite we are seeing a favorable result, unfortunately, our sample is not large enough to be able to sustain the claim. We would need most probably a few more individuals, and provided that the same tendency is maintained, then we might be able to show, to claim that there is an increase, an improvement in terms of skin luminosity. There is also a gray area in terms of the range of values from 0.05 to 0.1. So when the p-value falls between this range, within this range, we tend to say that the change is limit significant. So if I get a p-value of, for example, 0.065, I would tend to say that there is an increase. It's not statistically significant, but we have good indications that the product shows promise of being able to increase, to enhance skin luminosity. A few more subjects might be needed, 1 or 2. We have got a very good indication, but we are not yet there. Unless if in the study protocol, it's already mentioned that instead of 5%, we are going to use 10% significance level. Some studies accept this rate of error. So if the study accepts this percentage, then straight away, when we get a value of 0.065, that is 6.5%, it's less than 10% level, and we would say that the change is statistically significant. So this is how you would normally go about doing a comparison of two time points time point 1 versus time point 2. So I hope that you have enjoyed this video. I will try to make a few more, maybe not so long, just in bits and pieces, so that it can help you to understand statistical components of a report and to write some interpretations. Thank you.